Academic Engineering 757, Polymer Rheology, H.H. Winter, Lecture 13A. When you look in the literature for rheological data, you will find the same plots again and again. It's actually very hard to, or it was very hard to characterize a material rheologically. It was very hard to get a relaxation time spectrum. In the meantime, this has become routine in the last 2 or 3 years, especially with Michael's efforts and Polsowski's efforts. We put all of this on a computer. And all you have to do is to get a very nice data set, a set of G prime, G double prime over wide frequency range, or maybe many temperatures. And when you have that type of data set, the spectrum can be calculated in an interactive mode in about half an hour. And there will be a flood of data in the future in the literature. I think everything has changed in rheology, and that's nice because now we can do the important things. We can, for instance, use a spectrum and model some transient flows, or that's one subject I will talk about today. Or we can look at the relation between molecular architecture and the relaxation behavior of polymeric materials. And we will talk about this also today in a special case. So it's nice to come to those subjects, while 2 or 3 years back we mostly were grounded by some less important things, less interesting things. So the first subject I want to talk about is the testing of the relaxation time spectrum in some transient experiments. And that goes something like this. You choose a polymer, you get a polymeric sample, and you measure the relaxation time spectrum Gi lambda I over some finite number of modes. And that will be the linear viscoelastic characterization. The second step then is the performing of a transient experiment. Transient shear experiment is most easily done, but maybe extensional flow experiment. So you perform a real experiment at some temperature T0. Make sure you have data at temperature T0. Let's say you're shifting your data to that specific temperature level. And then, for instance, you do creep and recovery or stress growth and relaxation or any other transient experiment. And you calculate then, using the spectrum, you model your experiment. Here you have your transient data. Here you have your predictions from the spectrum. And then you compare the two, and you can see whether the spectrum is all right. So we, having those tools available, we can raise the confidence level of our procedure, which is very, very important. Otherwise, if you just measure, say, G prime, G double prime, who would tell you whether your data are reliable? But if you measure G prime, G double prime, get the spectrum, and predict some transients and measure transients, and all of this falls together, then you know that data are self-consistent and you can proceed. It happened to us that we got a new rheometer in the laboratory, and we measured some material functions on the new rheometer and also some on the old one, and there was a big disagreement. In the beginning of, actually we didn't check our data. We just trusted that the new rheometer would give fabulous data. Everybody moved to the new rheometer, like ours. And then we found that there's a factor 8 between the data on the new machine and the old machine, and we thought, oh, now our old machine is wrong, and we published the wrong data for a long time, and now the new machine really is showing that. But what happened was that the old instrument gave the reliable data. They had been checked, and the new machine had some problem with the hardwiring on the board. So we shipped the hardware back, and then we got this replaced and got perfect agreement between those machines. But the computer modeling in this case gave us the indication that there was a problem between the two machines. And this cross-checking is really essential in rheology. One experiment we could pick would be stress growth in a shear flow followed by relaxation. The strain which we would prescribe is actually the strain rate which we would prescribe would be 0 all over, except for a flow time from 0 to T0 the material is deformed at a constant shear rate. Otherwise, otherwise the sample is at rest. Now, this period contributes then to the Boltzmann equation. Here's our integral from minus infinity to t, but only the period from 0 to t0 contributes in this Boltzmann equation. We replace now the relaxation modulus with the finite sum of relaxation modes, which we would get from our characterization of the sample. That would be the result of G prime, G double prime experiment plus processing of data. So we know that spectrum for our sample. And we can integrate this very nicely. That's a major advantage of using Maxwell modes. If you have those exponentials, you can integrate them very nicely and get the stress in analytical form in terms of some exponential functions. And you have to sum those exponential functions. All of this is on the computer program. Actually, I am planning to have one session on the computer where I demonstrate all these features to you. But the computer in this lab, in this studio, is not strong enough. I have to go to the other computer and pre-record that, and then we can play it back and do this. So the processing of the data plus the modeling I'm talking about today will be in a session when we will go through that. You will see how easy that is now. Okay, so that type of startup we would like to study now in a real experiment, and we will take 3 samples. We take a PDMS material which is able to cross-link, and we cross-link it a little bit, and we get a viscoelastic liquid. It's a highly branched, fairly high molecular weight material, but it's a liquid. It's relaxing, and I already show the relaxation modulus to you. I don't show G prime, G double prime, and so we didn't really measure G. We measured the dynamic mechanical data. And the next one is a sample at the critical point, at the transition from liquid to solid, has a modulus which is something like this, and the third sample is a solid. And for all of those, you can calculate the relaxation time spectrum. You have those handouts from last lecture at the end, so you will find those in your files. Don't worry about this. So we have 3 materials here, and we know the spectrum because we have supposedly have performed those experiments. And then we look at them in a shear experiment. A shear is, say, from 0 to 10 seconds at a constant shear rate of 0.003 seconds to the -1. And we look at the stress response now. The stress is growing in the solid because the stress is somewhat proportional to the total strain, and the strain grows linearly. And then when the flow is stopped, the stress somewhat relaxes, but not very much because we're talking about a solid. And you're looking at 3 experiments. The data points are compared to the model. The lines are given by the models here. At longer times, the strain is getting large, and there might be some deviations already because we are moving out of the linear viscoelastic region. Now, a second experiment, which I already have here, I didn't go through the modeling procedure. You could do that as an exercise. In this case, we would have a load put on the sample between 0 and T0. So constant shear stress is imposed. Otherwise, there's no load on the system. So we're talking about creep during this time and recovering for a longer time. The creep is giving us a transient strain here, and the strain is somewhat leveling off, keeps flowing because it's a solid. And then when we turn off the stress, the material recovers, and after long times, it will go back to its original shape. So that's what we would expect from a solid, and the modeling and the experiment is in pretty good agreement. For the liquid now, we would have a stress growth when we start up the shear flow at constant rate, the stress growth here, and then the steady shear flow reached. And then when we turn off the flow, the sample is at rest, and the stress relaxes down to 0 as it should for liquid. You can see there is a reasonable agreement, but it's not perfect. And then in the other experiment, where we look at the strain, this is talking about gamma here, as a function of time during the imposed stress. Now, if you have a stress, say, from 0 to about, 50 seconds, then the strain grows, and then there's a linear growing, that's a steady shear flow region. The stress is constant, and the rate of strain is constant. And then when turning off the stress, the fluid somehow goes back a little bit, it recovers, so it has a negative strain, and that would be called the recoverable shear of that material. You can calculate that, and it's coming out of the model very nicely. Excuse me? This here, this tip? Oh, this tip is due to the stopping of the experiment. You have a stress from 0 to T0, and then at this time you take off the stress, and the polymer has been deformed by the stress was on there, and then when you take off the stress, it bounces back a little bit very, very quickly, and then due to this is for the short modes, and then for the long modes, you need some longer times to recover. Actually, if you would have a relaxation spectrum with a single mode, it would just bounce back instantaneously and stay there. But the interference between the different modes gives you a broad distribution of the relaxation or the part of the recovery in that experiment. Maybe we can do an exercise where you see what the difference is between a single mode behavior. It's very popular to use a single Maxwell mode to describe the transient processes. So see the difference between a single mode and a double mode. And double mode is qualitatively different from a single mode behavior. The third material was the one in between, the one near the liquid-solid transition. We call that the critical material, critical gel. And that somehow has intermediate behavior. The stress grows in a power law format. This is a parabola. And also in a creep experiment, the strain grows in a parabolic form. And we can solve this type of problem for the ideal behavior at the gel point. We will talk about materials at the gel point in greater detail. But in this case, we did not worry about specific behaviors. We just looked at G prime, G double prime of those three samples, got the distinct relaxation modes, not caring whether it's a liquid or solid. Or in our window, we just got the representative modes, and we are using those in the modeling. Now you can see that the predictions are visible. If I sum this up, it's pretty good agreement between experiments and the predictions from dynamic mechanical data. And see, that's not bad. You're doing a dynamic mechanical experiment, and you're predicting startups and all kinds of other functions. You have to appreciate that, I think. Now, the time window of the spectrum has to include the time window of the experiment. So we have to be aware of the limited information we have from G prime, G double prime data when we model experiments. We couldn't model the creep experiment, which lasts a day, if we have data only in the second range, okay? Except if we have a material which has a short terminal zone and a terminal relaxation time and all this. Okay, so that's one thing we can do with our relaxation spectrum. We can model all kinds of transient experiments, and that's very easy to do. The next subject I want to discuss is the relation between relaxation time spectra and molecular architecture. It's one of the classical questions in polymer physics. Now, I will talk about the rest of the lecture here about the long linear flexible molecules, a very specific architecture. So, but in general, we have to solve this question. We have to relate the architecture to the spectrum. And until recently, we didn't get the spectrum. It was very hard to get the spectrum, so we couldn't do much work in this area. But now we are just plunging ahead. It's so easy, and you will see that. The tremendous advances in recent times. The approaches to solve that type of problem are like this. In molecular dynamics, a theoretical physicist would propose a model for molecular motion and derive the set of relaxation modes from that. He would describe the motion of the whole chain and parts of the chain and small segments, and according to that he would look at the different different relaxation modes, the long modes associated with the large length scales in the system. So that would be covered in molecular dynamics, and maybe we will have Muthu giving us a lecture on molecular dynamics to fill that subject. I will approach that as an experimentalist, where we would perform well-defined experiments, say dynamic mechanical experiments, and analyze the data as discussed, and then we look for a pattern in the relaxation behavior. If the polymeric material we are using is well-defined, then we can expect that there's some systematic pattern in the relaxation behavior, and then we can pick that solution from our experiment directly. This works very nicely for polymers which have long linear chains of uniform length and chains which are flexible. Let me maybe draw a cartoon here, what I mean with flexible chains. Here, this would be a flexible chain here. It would be linear, it would be randomly coiled. And if you take a small segment from that chain, which you would have to draw in carbon bonds or some distribution, basically you would see a curvature here, local curvature in that chain. And flexibility requires that the radius of curvature is much, much smaller than the length of the chain. And that's what we are going to talk about. Very, very flexible molecules. Now, for those molecules, we will look at the relaxation behavior of the melt, and there focusing on the entanglement regime and the flow regime of that system. I'm not going to talk about the glassy behavior. That would be a lecture by itself. And I'm not the specialist in that area, so I could talk about this, but it's much more fun to talk about this since we are working in melts ourselves. So I will talk about this, and also polymer solutions from those monodisperse polymers are interesting to look at. You all know that the zero shear viscosity of such a well-defined system depends on molecular weight. At low molecular weight, viscosity grows proportional with the molecular weight, and then above a critical molecular weight, it grows with a 3.4 power, and we would say the polymer is highly entangled, and here it is too short to form entanglements. Nobody has seen entanglements, but it's a convenient way of saying that there's some connectivity between the molecules, which makes the material behave network-like at intermediate timescales, make it behave like a rubbery material. So above that molecular weight, characteristic molecular weight, we would expect elastic behavior, and that's the focus of our experiment we're going to talk. There's some references on melts. I will use experimental data from our own laboratory here and analysis from here. On solution, Colby and Gressley have a set of interesting data which we could look at. And then molecular dynamics is very involved. Classical papers of Raus, and then of Doyen Edwards and Dejean. And then in Bird, Armstrong, and Hassager, the textbook we are using, the second volume is concerned with molecular dynamics. And then Dick Clouzot has newer theories, the double reptation model, and Gressley and Pearson, and there's a whole range of physics people. Now, I'm going to concentrate in the experimental part, and hopefully maybe in a guest lecture we will be able to look at the theoretical approach. Our approach goes something like this. We will use a well-defined polymer, monodispersed material. It's not perfectly monodispersed, but it should be close to monodispersed. And we hope that this small deviation wouldn't hurt us. And in fact, it doesn't. We can see that from analysis, that we are close enough to really observe monodispersed behavior in our experiments. So we take those samples, measure G prime, G double prime, and analyze the data and hope that there is a systematic pattern in the relaxation behavior, some simplicity in the relaxation behavior. That's what we are looking for. And then we go to our friends in physics and ask them why is it like this? Why is there a pattern in the relaxation behavior like that? The material which we are going to look at is polystyrene. 6 samples had been studied. We didn't even have to measure this ourselves. Alois Schausberger performed those experiments, published them in '85, and he also visited us a year ago. So we had all the information available. It was a very intense time when he was here. So we looked at his data. We have data ourselves also, and I will talk about those. But let's just look at the data of Schausberger here. And I will have a little size change, Becky. We have a few graphs which are a little bigger. Now, this is Schausberger's set of G prime data. He has linear molecules, and when he makes them longer and longer, you're not cooking the short spaghetti, you're cooking longer spaghettis and bigger spaghettis. And the question is, what's happening to the relaxation time spectrum? If they would be infinitely long, then your whole sample would be one linear molecule, basically, and the relaxation time would be very, very long and would be solid-like. But as it turns out, when the molecules get longer and longer, the plateau modulus stays constant, but the cutoff time goes to lower and lower frequencies or longer and longer times. Now, this is the typical feature for G prime, and the typical feature for G double prime is also the extending here of the spectrum to lower and lower frequencies. Remember, G prime and G double prime both contain the whole information of the spectrum. So it's also stretched to lower frequencies, longer times. And the characteristic now for G double prime is the terminal zone here goes down with a slope of 1. G prime was going down with a slope of 2 in the terminal zone. Then there's a breakpoint at the characteristic relaxation time. And then there is a stretched region, a linear region here, which is characterized by some slope. Let's call that slope n. So its slope is minus n here, but it's somehow characteristic for the material. And then at a shortest time here for this region, there is a transition to the glass. Before I introduce some notation, this would be region 1, the flow regime here over, in this case. This would be the entanglement region, would be region 2. And then region 3 would be the transition to the glass, and region 4 would be the glass behavior itself. And we are mostly interested in region 1 and region 2, the flow regime and the entanglement regime. That's the type of region we would like to model. So let's take Schausberger's data now and shift them all on top of each other so that we can compare the terminal zone. And this is G prime, G double prime, and note for the low molecular weight, the upturn was very soon, the entanglement region was very short, and then for the 2.5 million, for the long molecular weight, we have this long region. But you can see that the spectrum is really the same for all of those materials, and we could just look at the spectrum of the longest molecule of the 2.5 million. And if we know the spectrum of that material, we can include all the other spectra. We know those. Okay? This is also obvious for 10 delta. And showing you the loss tangent of that same system, you see the flow region here having a slope of -1, because G prime goes with omega squared, G double prime with omega, and when you take the ratio of G double prime and G prime, you have a slope of -1 here. Now, this is the region where G prime is constant about, and G double prime goes down with -n. So this is a slope of -n, right? And then for the glass, it somehow goes up. Again, all the curves are shifted into their terminal zone. That's why those upturns are seen here. We really we are interested in the shape of that curve. That's what we are interested in. And now we would like to see how the conventional theories are doing in describing that shape. We will use several equations, several models, and calculate those curves now, G prime, G double prime from those models, and see how well the fit is. The most simple model would be a Maxwell model. We would just take a single exponential decay. We wouldn't expect too much. We know we need a spectrum of relaxation times, but it's good to have just a single mode. And the second model I'm going to use is the stretched exponential. It's also called the Kohlrausch model, or you could call this a Kohlrausch mode. It's very popular to describe relaxation phenomena of glassy materials. And I'm not talking about glassy materials here, but you will see for the entanglement region, for polymer melts, it's not suitable. It will not give very good results. But you will see this in a moment. And then we also will use the Rous model, prediction from the Rous models, where a specific shape is really prescribed, because in the Rous model you only have two parameters, the font factor here and the longest relaxation time. If you change those, you shift, say, if you change the font factor, you shift your spectrum up and down. If you change lambda, you're changing your time scale, you're shifting your spectrum sideways. But the shape of the Rous spectrum is prescribed. You cannot change the shape by shifting, by changing the parameters. So we can compare the shape of the Rous model with the shape of our experimental data set and see whether there's any chance of fitting that. The same approach we will apply to the spectrum of Dejean and Doi and Edwards, where again two parameters are used, the font factor and the longest relaxation time. Again, those come out of molecular arguments, but I'm not specifying this in the moment. I'm just looking for the shape of the material. And again, if you would change lambda, we would shift our curve sideways, and if we choose G, we would shift our curve up and down. But the shape of the Doi-Edwards spectrum is unique. There's just one shape, and it either fits experimental data or it doesn't. So let's look now at experimental data, at the data before, and we will just take the data from the 2.5 million sample data of Schausberger. You can see G prime and G double prime. Neglecting the upturn, the glass transition is not the focus in the moment. And this will be now our reference. The first curve which will be challenged is the Maxwell curve here, the predictions from the Maxwell model. And you can see when putting this on top here that the Maxwell model does very well in fitting data in the terminal zone. It's actually amazing how well a single mode describes the relaxation spectrum in this flow regime. But you see that in the entanglement region, there's no chance. You need many modes to describe the spectrum. A single mode model is never able to cover the experimental region. Will never be good enough. So how about a stretched exponential? There are some people really favor stretched exponential, and you could say if we have an exponent, let me point this out here, an exponent beta here, which is not 1. 1 would be a Maxwell model, but if we make it some fraction here, it's 0.55, our transition is a little more smooth, and we can accommodate, for instance, G prime very nicely. See, this is a pretty good fit. But G double prime will not be fitted. And somehow there's too much curvature in there. It's not, the basic shape of the stretched exponential is not good enough. Somehow we have to go to lower exponents to get a better fit. So let's go to 0.35. And let me see how we are doing. And now you see we can fit maybe over here in the entanglement region, but we are sacrificing the terminal zone. Whatever we do, we will fail. We will not be able to model the experimental data with the stretched exponential. And that's just a simple fact to recognize. It's not more, not less. It just tells us that the Kohlrausch mode is not able to describe entanglement and flow region of a polymer melt. So any physics which will result in that type of spectrum is not realistic. And some people derive physics like that and talk about the mode coupling and very complicated systems. It is not suitable in the flow regime and the entanglement regime. It might be good for the glassy regime. I don't know. I don't have good data in that region. If I would have good data, I could show you the spectrum immediately. We would, within half an hour, we would have the spectrum. We would find interesting pattern and we would be moving. But it's very hard to get good experimental data in the glassy region because your sample is out of equilibrium. When you lower the temperature below Tg, your coils are in a state which is not the equilibrium state. And then you measure G prime, G double prime in some out of equilibrium state which depends on thermal history, and you can get anything. So that's a real challenge maybe for you. So if you give me good data, or actually if you have good data, you work in our lab and you process them yourself and you'll find, you know, whether Kohlrausch modes, for instance, describe the glassy behavior, and there you are. And then you have the problem solved. Here I did some calculations on a variety of Kohlrausch modes, and you can see they're all giving lots of curvature and no hope really of describing the spectrum. Now the biggest contender is, of course, the Dewey-Edwards spectrum. Let's see how that spectrum is doing. We take our data set. Again, let me adjust the data here to the middle again. And then we put the Dewey-Edwards spectrum on top. And remember, we can shift it sideways up and down by changing parameters, so that's not the point. The shape is, but I shouldn't rotate it. I'm only allowed to, to go up and down. So you can see I can fit the terminal zone very well with that spectrum, but in the entanglement region, you have disagreements which are easily order of magnitude or several order of magnitude. So the entanglement region is not described by the Dewey-Edwards model. And I don't know why. It's a big puzzle. There's a lot of enthusiasm coming from this model and a lot of physical relations which have been derived from this model, which are very helpful, which constituted a big progress in polymer physics. But if you want to be quantitative in that specific case, you will see that it doesn't fit. And that's the effect which Dewey and Edwards mention in their book themselves. So there are lots of attempts of modifying the classical Dewey-Edwards spectrum to mend it. And with a lot, with very complicated correction terms, I think you can make it fit to the experimental data. But it requires some modifications to accommodate for that. One more candidate, which I haven't mentioned yet, and that's the Rheau's model, the classical Rheau's model, and that's very, very interesting. I will again use the experimental data, and you will realize immediately that the Rheau's model gives a nice description of the terminal zone, but then immediately goes up. And this upturn is known from the glass transition temperature. So the Rheau's model describes a material at about the critical or the characteristic molecular weight, or a polymer near the entanglement molecular weight. It's not long enough to form entanglements. So it goes from the flow regime, from regime 1, directly into regime 3. Okay? And that transition is performed actually quite nicely with the Rheau's model. The slope here might be different for the glass, but still it's a very powerful way of doing that. Okay, now how about ourselves? How about us coming in now with a new approach? We just take Schausberger's data and we calculate the spectrum. See, and that's what we did. We calculated the relaxation modes, and we are looking for some pattern. So this is the spectrum calculated. We are looking at the short modes here, behavior at short times, and behavior at long times, and then there will be a cutoff beyond which no relaxation behavior is being seen. The material with the longest relaxation time, the material with 2.5 million molecular weight, has this spectrum here. This is 2.5, this is next lower, and you can see how they go. I'm plotting GI as a function of lambda. So those, we're talking about individual Maxwell modes, and this is the strength, and this is the time constant of the specific Maxwell modes. So all the Maxwell modes which describe the glassy behavior are along this line. And then let's talk about the longest molecules here. All the Maxwell modes for this molecule sit also on a straight line here. By the way, the slope of this line is in. That's the slope we saw in G double prime. It's not a new, nothing new coming in. It's this slope. And also note that the spacing of those modes is fairly regular. Now, in our analysis, we didn't prescribe the spacing of those modes, and you can see they are at some odd positions, somewhere intermediate between the interval. But the material somehow chooses the modes to be most efficient in the fitting when they are spaced equally along that line and when they're sitting on the strain line. So there's a pattern in that spectrum. We have looked at other materials, and we know what that type of pattern means. It means that the spectrum is really a power law spectrum, and we can convert this spectrum immediately into a continuous spectrum. That's so that was within 2 or 3 days we moved ahead and had the solution available. One other thing to note is that the top of those is always at the same position of those points. And then the cutoff is somewhat gradual, but the gradual transition here is an artifact of our discrete representation of the relaxation spectrum. So if we go now to a spectrum which is continuous, then the cutoff will be sudden, will be abrupt, but we maintain the slope of the curves. Here, let me move it in here. We're plotting H as a function of the relaxation time. So you see all curves have the same shape. Talking about the same shape, the same slope here, and the top point has about the same height, and then in this region there's already interference with the glassy region. The slope of those lines is about a quarter. It's about 0.2, 0.25 in that order. We don't know whether it's a material parameter or whether it's a universal constant. It would be nice to have universal constants, of course, but we have to do more experiments to find out about this. So, but this is the spectrum, and it has a very nice pattern. It's, I mean, this is, it couldn't be more simple. If you take off the glass, for instance, I'm covering this. If you just take this region and then neglect the transition to the glass, if you continue this, it is just a straight line which is needed to describe the relaxation behavior of the material. Now, we are getting this from modeling our data, right? And now let's use that and see how well this spectrum, this very simple spectrum, how well that spectrum fits the experimental data of Schausberger. And you can see the lines drawn through here, G prime, G double prime. Remember, before we looked at the same spectra, and you saw orders of magnitude differences between models and predictions. And here, the simple spectrum gives lines which go right through all data points. Because it's because that spectrum is really a representation of our experiment. It's nothing else. It's just a translation back and forth. Now, this is for G prime, and the same type of fit you can see in G double prime. And again, you can see the spectrum. Now, the spectrum which we proposed here, just this linear spectrum, we call BSW spectrum because of Baumgaertel, Schausberger, and myself. So we humbly put our name on that immediately. But also, it's kind of long. We didn't know how to call it. There are many different spectra to compare to, so we just BSW and then we kind of know in the lab what's meant. We will talk about some other spectra. Now, how about the cutoff? You know, the longest relaxation time. The spectra had always been cut off at the longest relaxation time, and this cutoff had been calculated by reducing the data. So we can plot now the longest relaxation time as a function of molecular weight, and you can see that this follow a straight line of about with a slope of about 3.45. Okay, so that's the spectrum calculated from that system. And just to sum this BSW model up, here this would be the spectrum we are going to use for the flow region. We have the cutoff, that would be region 1. This would be region 2, the entanglement region. This is region 3 to the glass, and then something happens here for the glassy behavior, and I don't know in detail. So we can write down a mathematical equation for that type of model. We could say for the spectrum is given by a power law. Now, for the entanglement region, we have this type of power law, front factor, and then this time constant, and the slope, which is a quarter about. This is given in G double prime, and this is the power law which we see for the glassy region. This is the slope down, and this is the slope up, and we're just adding those two in a linear superposition. That's the most simple way of doing it. Another approach would be adding them in the log-log plot. Since we are plotting everything in a log-log plot here, so we would just put this line, we add this value to that line, and then we have the transition very nicely. So if you're adding this in the log plot, you can contract this here, and h of lambda would be then the product of the two. And you can do everything really you would like to do in this case. And another observation I wanted to discuss with you, and that's the following. Coming back to our data here, this is G prime, G double prime. I take the spectrum now and put it on top. Here, this was the spectrum. I had h of lambda, and I put it on top of our data, G prime, G double prime. So if you please show this here, I put it on top. Yeah, Becky, if you please see, I'm putting this. Yes, she's gone. She went. Becky, can you show it, please, here? Okay. You will see that the spectrum reproduces G double prime in great detail. No, she's trying. I don't know. Can you switch the here the please show the no? Shall we take a break? Yes. Okay. Let's take a break. Maybe Becky was taking a break already. Chemical Engineering 757, Polymer Rheology, HH Winter 13B. Since we are looking for patterns, let me show you another puzzle. So this is the data set. We still the Schausberger data set, polystyrene at 2.5 million, G prime, G double prime. And we compare that now with the spectrum. This is the BSW spectrum I'm using, and I'm just turning it around because omega is 1 over lambda. So we have to turn this upside down. And then I'm putting the BSW spectrum on top of G double prime, and you can see there's a perfect match. See? And then there's a cutoff here. This is the cutoff time, and you can see also that the cutoff for the flow regime is not at this crossover, but it's moved down here to 1 over here. So it's just an interesting observation. You could take this curve and take it as a first guess for your h of lambda, just flip it over, and then start your calculations, improve it, and see how it fits. So that would be a simple way of getting h of lambda. Now, all those results have been derived from a polystyrene, and I have to show you that it's not just associated to that specific polymer. So we took some data ourselves of polybutadiene samples, which we got from Shell, from like Masi and Joe Machado. And it will appear now in Rheology Acta. So we had molecular weights from 20,000 to 200,000, highly entangled molecular highly entangled polymer melts. We measure G prime, G double prime. Again, the same feature. With increasing molecular weight, the plateau modulus stretches, and then slope of 2 for G prime. And for G double prime, the same features again. You have a slope here, which is about a quarter in this case, and cutoff, and a slope here of 1 for G double prime. And then again in 10 delta, again the same pattern. Flow regime -1. This is entanglement regime is -n slope, and this is the transition to the glass. So it seems to be a general feature of linear molecules. We calculated the relaxation time spectrum for this material, and here you can see the set of those relaxation spectra. Again, it's the same features, and here we have individual data points in it, and they are already calculated, by taking the individual modes and dividing them by the log of the spacing. We get the local HI values, and then you see a very nice agreement. The truncation at short times gives some disagreement here, so we just need more about the glass. But here the agreement is very nicely, and you also can see the finite spacing gives rise to a more gradual distribution of modes at the end. So all of this is consistent. Yes, question? Oh, the question is what means PM spectra? That means parsimonious model. This is the approach where we take just a few Maxwell modes, as few as possible, to describe G prime, G double prime. And we used the parsimonious model in the beginning to analyze our data and to find a pattern, systematic pattern in the system. So that was the starting point. But now, since we know the BSW model, since we know this general shape, we don't really need the parsimonious model anymore. We can use that spectrum directly. We're independent of the conversion method now. But still, it's nice to compare the two approaches. Gives us more confidence about the parsimonious model. You can see how powerful it is, how nice it is able to helps us calculating things. The cutoff relaxation times, again, follow a slope of about 3.4. These are for the 4 samples, and the 3.4 power is put into the axis here on the side. So no surprises. It's really the same behavior for the polybutadienes as for the polystyrenes. We also had a polyisoprene standard, and as you might guess, here, typical feature, linear molecules. Again, we have a fit of the data with the parsimonious model, and with a two power laws with the BSW model. And you can see that the parsimonious model is a little better because locally you can fit data with some local adjustment of those Maxwell modes. While in the continuous spectrum, you have only very few parameters to adjust. So it's, but the agreement is just going all through here. And this is the spectrum of the polyisoprene standard. And again, you see the perfect fit. The green ones are the GIs, and when they are normalized with the spacing, you see the red dots. And again, the spectrum has the same features. The slope is a little smaller than 0.2 here. We don't know whether this is real or where this comes from. We got a polyethylene sample of about 100,000 molecular weight from Enrique Valles, and again, G prime, G double prime, same spectrum. Spectrum can be calculated. It's hard to get a spectrum over many decades for the polyethylene, and again, line spectrum is giving us pretty good agreement. We had the lines through in the data which I just showed before. So going through all those materials fairly quickly just to show you that nothing specific is to be expected. Now we still have to look at our experiments, and for the polyethylene it was, for instance, interesting that the crystallization behavior was slowed down of that sample. So we assume that in that model polyethylene there were some double bonds in the chain. It wasn't a perfectly regular polyethylene. So during heating, this is a G prime, G double prime measured at one frequency, and we're heated at a certain rate, 2 Kelvin per minute. And when we're heating, it's melting somewhat, and then when we're cooling, it stays in a liquid state. It's in a supercooled state. Normally, polyethylene crystallizes very fast. So we assume that for getting tailored molecules like this, one had to sacrifice a little bit in the structure. But still, linear chain, flexible, and the same time of behavior. Now I want to come back to the Doi-Edwards spectrum and compare that with the BSW spectrum with a slope of 0.5. See, if we take a slope of 0.5, then it's somewhat the spectrum compares somewhat to the Dijen, Doi, and Edwards spectrum, because at long times, or at short times, and when you take many modes, even the shorter modes, the slope is 0.5. It's a scaling behavior which comes in there. But still, the prediction is lower than you would get from the BSW spectrum. So that's a big difference. We find a slope of about a quarter, 0.25 or 0.2 for most materials, and here 0.5 is somewhat too steep. So the Doi-Edwards model probably gives the lower bound of that spectrum. It just says that molecules are not able to cross. That's a hindrance. But something else has to enter in the model, some other dissipation mechanisms which then increase the value of G prime, G double prime in the entanglement region. And the question is, what is that? What additional physics has to be entered in that? Let me also come back to the Rouse model, which looked something like this here. And this is not only the Rouse spectrum, in this case G prime, G double prime. This is the blue curves here, Rouse spectrum as a function of frequency, but also a power law spectrum drawn on top. And this power law spectrum looks very simple. It's just the glass, the h of lambda. You can leave the scale, that's okay here. It's just h of lambda for the glass. Remember, entanglement regime would come in like this. It's just the glass, and it's cut off at its longest time. We're talking about a molecule which is at its entanglement molecular weight, but it's not longer. It's not able to form entanglements. And when you take this spectrum, of course, with a slope of minus 0.5 because of the 1/2 exponent in the Rouse model, if there would be another exponent, you could take another slope. So if you just take this and calculate G prime, G double prime, you get exactly the same spectrum as shown in the as calculated from the Rouse model. It's interesting, isn't it? You just take a simple power law, cut it off, and you get the same, exactly the same behavior, same structure. And all of this fits together very nicely. Okay, I hope you probably saw more than you wanted to see, more of those repeated data. But I want to convince you that it appears with all linear chains, this type of spectrum. And now I want to explore with you the properties of that spectrum, of the BSW spectrum. And we will not take the glassy transition into account. We will just take the power law, straight line in log h over log lambda, cut off at the longest time. That's what we would like to look at. Now, I myself preferred looking at the relaxation modulus. So far, in rheological modeling, I just needed a relaxation modulus to put into the Boltzmann equation, and I could calculate transient stresses, and everything would be fine. So h of lambda was a nuisance for me. I just didn't need it. But the data processing, the calculation of relaxation spectra, told us that we should look at H, because in H there is a very simple structure, a very simple pattern, which somehow has to be related to the physics. So because of our data conversion methods, I'm teaching about H. I think last year I hardly mentioned it, or 2 years ago I probably didn't. Maybe it was half a minute I talked about the relaxation time spectrum in terms of H, and everything was in terms of G. When you look at the book of Bird, Armstrong, and Hassager, everything is in terms of the relaxation modulus. They hardly mention the spectrum, because for modeling they don't need it. But polymer physics somehow tells us that this is where the action is. That's where the prediction should be. But even the Rouse model predicts G of t. The Doyle-Edwards model predicts G of t. They all go for the relaxation modulus. And the question is, why should we look at H? Why is that the important function? Okay, so let's work with that relaxation spectrum a little further with H. We will take just this power law and say it's given by a front factor times lambda to the power n. And this spectrum would hold for lambda smaller than lambda max, n is equal to 0 for larger times. We are neglecting the glass transition in everything we were doing. So everything in the following, all the modeling, will concern only the flow regime, region 1, and the entanglement regime. It will not concern anything else. Okay, so we're just focusing on that. The first thing to calculate would be the plateau modulus, because that's an important material parameter in G prime. So we would take the from the calculated modulus, which I'm plotting here, we would calculate the plateau modulus, which is really an extrapolation of the entanglement regime to 0 times, neglecting the transition to the glass. So it's an extrapolation of the region 2 behavior. Now, this plateau modulus is defined, for instance, there are many ways of defining it, but they all result in the same equation. So it could be defined as the modulus here in the limit of 0 time. We would describe the modulus in terms of the spectrum, where the modulus is in the integral from 0 to infinity of the spectrum times e to the minus t over lambda, d lambda over lambda. And we take the limit for t equals 0. Now, this limit only affects the exponential function. It says that this exponential function goes to 1, and our model is really, our modulus is given by the integral h times dl over L from 0 to infinity. But now, when we put in our spectrum, our specific spectrum for the monodispersed material, we know it's just, this spectrum is just a constant times lambda to the n. And it is cut off, so the integration doesn't go from 0 to infinity, but it goes to lambda max. Beyond that is no contribution in the integral. The kernel of the integral is 0 at larger values of lambda. So we just integrate from 0 to lambda max, and you evaluate this immediately. H0 goes outside, and you find that the plateau modulus is equal to 1 over n times this constant. This is the fun factor we use in our spectrum, times lambda max to the n power. And we will invert this now, and we will use this equation to evaluate H0. See, the fun factor was just taken as something, some constant, and we didn't know what's the value of that constant in terms of our experimental data. But now we can express H0 in terms of plateau modulus n and lambda max, which we have already. And in the continuous form, we can now say that the spectrum is equal to the fun factor n times the plateau modulus times lambda over lambda max to the nth power. And this is for lambda smaller lambda max. And it's 0 for lambda bigger than lambda max. Now, often this is hard to integrate. You know, when you put this modulus into the Boltzmann equation, you run into all kinds of trouble. So we are often using a discrete form of that equation. We're just saying that the h of lambda is described by discrete modes, and they are given by the leading modes. I started the spectrum here with 0. The 0 mode would be the longest mode associated with the longest relaxation time. A is a spacing parameter in our case, and this is in the order of 0.5. It should be smaller than 1. And we use that. So for convenience, it's easy to jump to the discrete spectrum, do your calculation, and then use the result. And since we know that the discrete and the continuous are on an equal footing, it doesn't matter whether you do that or not. So knowing that spectrum now, we can determine the parameters. Let's say this is an experimental data set. Somebody gave this to you, or you yourself, say, measured G prime, G double prime, and how would you get the spectrum for that? You would simply take the plateau modulus here. This is Gn0, right? You just read it off the graph. You take the longest relaxation time somewhere over here. Lambda max is given here, so this is 1 over lambda max. This is the cutoff. And then you put in your slope here. This is minus n. Yeah? And then for the glass transition, you have something like here. This is 1 over lambda 0. And then you could take a power law, can take this slope here. It's in the order of, say, 0.6 or so, 0.7 for the glass. And then you're in business. You just plug it off the experimental data. And then you're writing down, you plot your spectrum. This highest point here has the value n times Gn0, so that's what we just determined before. And it has the value, I should have left it here so that you can see this. Okay. And it has the longest relaxation time. This is lambda max. Okay. And this is the slope, which we just determined. This is slope n. So independent of Michael's conversion method, you might not like this conversion, with all the Maxwell modes and the parsimonious model, and say, I prefer other conversions. And it's completely up to you. We don't need it here. We just draw parameters for the spectrum directly from the data, and are in business. We can do our calculations. So this is from exploring the plateau modulus. Now we find out about all parameters needed in our spectrum, and we know now what that is. So now we can calculate, for instance, the relaxation modulus of that system. That's the modulus we would put into the Boltzmann equation to calculate transient stresses and strain. So the relaxation modulus is given as an integral of a spectrum times e to the minus t over lambda d lambda over lambda. This is a general formulation. In specific now, we put in our form here, the power law form, the self-similar spectrum, and integrate from 0 to lambda max. This is to make sure that we have the cutoff. And of course, the exponential function is needed here. I put this outside. And then you substitute, somehow you say that X would be described as lambda over lambda max, and you find that this is an incomplete gamma function. It doesn't have an analytical solution. It's quite nasty. So by in the most simple approach here, the most needed function for our modeling, we already don't have an analytical solution. But it's no problem, since we would represent this spectrum with a discrete set of exponential discrete set of Maxwell modes, and then do all our integrations which are needed. The reason for not having an analytical solution here, or not having an analytical solution here, is probably the reason why nobody saw the spectrum before. See, if there would have been an easy analytical form in G of t, it would have been obvious in previous cases because everybody was focusing on G of t. Now, what would happen to our relaxation modulus if the chains would be made longer and longer, if lambda would be made infinite, very long chains? So the modulus now, in the limit of lambda going to infinity, we would take again the same integral we had before, and in this case we can come to an analytical solution. We just substitute x again here for lambda over lambda max, and then the only term where lambda max occurs is down here, and if we take lambda max going to infinity, this exponent is 0, so this function reduces to 1, and the constant is put outside, n times the plateau modulus, and then e times the integral from 0 to 1. See, going from 0 to lambda max with this new substitute goes from 0 to 1 times x to the n dx over x, and when you integrate this, you will find that the n cancels and the modulus is equal to the plateau modulus. That's what we would be expecting. Like in G prime, we know that the plateau is getting longer and longer and longer to 0 frequency if the molecules are made longer and longer. So that result is really consistent with all the experimental observation. So it's nice. We're kind of looking for self-consistency. So it's, you know, it's such a simple equation. I would like to know, does it violate any observation which we make otherwise? The third quantity we would like to calculate are the dynamic moduli G prime, G double prime. We just put the spectrum in here, integrate from 0 to lambda max, and again there's no analytical solution. That's why even from G prime, G double prime, people did not see the simple spectrum. That's why it was kind of hidden. We needed the parsimonious model as an eye-opener, and now where we know what to look for, it's quite easy. How about the zero shear viscosity? We know the zero shear viscosity is given by the spectrum integrated from 0 to infinity. We put in the BSW spectrum, integrate now from 0 to lambda max, and this has an analytical solution. The spectrum is given just as a product of the modulus times the longest time times a front factor, which depends on n. And n is a quarter, so you can evaluate this. But now let's invert this. See, we never really knew where the longest relaxation time was. You know, it's not at the crossover of G prime, G double prime. It's somewhere at a frequency lower. So the question is, how big is the longest relaxation time? Can you get the longest relaxation time in a simple fashion from your experimental data? Well, you can with the solution which we just determined. We would just express everything. We rearrange the previous equation. We are going to rearrange this equation, put lambda max on one side, everything on the other side, and find that lambda max is just given by the zero shear viscosity, which you could determine from your data directly, divide by the modulus, plateau modulus, and then have this factor behind. And if n is 1/4, the factor is about 5. So we have 5 times the ratio of zero viscosity divided by plateau modulus is the longest time. Isn't it neat? I mean, this is quite a nice result for so much for simplicity when you're getting this longest time immediately. Now, how about the steady state compliance? That's a property we haven't talked about much, but it's a quantity which is very sensitive to small changes in molecular structure. It's defined something like this. The compliance is given by the slope of G prime at in the approach of zero frequency. You need the terminal zone. In there, if you divide by omega square, you know, in the terminal zone, G prime goes with omega squared. So the ratio of those is independent of omega. So this will be a constant, and this divided by the square of the zero shear viscosity. Let's evaluate this function now. We would take G prime, as defined before, take the limit for omega going to 0, and we're dividing by omega squared when we take the limit. Now, in this function, if omega goes to 0, this group is much smaller than 1. So we can just neglect this, and our result is just h of lambda d lambda, and this is this function. And from previous calculations, we know that the zero shear viscosity is given by the integral of h of lambda d lambda. So when you compare those two, there's a lambda more in, and we are now going to integrate this, or first, before putting even the spectrum in here, we redefine our zero shear compliance as this integral having h lambda times lambda divided by that integral where we just have h integrated and taking the square of that. And if you evaluate those two parts, you will find this is the h of lambda times lambda evaluated, find an analytical solution, and you divide this by the viscosity and find that the compliance is given here by the ratio of those two results, and you rearrange this to find now JE0, you know, and GN, the plateau modulus, are put all on one side, and everything depends on n here. So the product of the two is 1 plus 1 over n squared plus 2n. Now, the Doi-Edwards model in its classical form predicts that this is equal to 1. But people know that this is not true for experimental data, that it's in the order of 2 or 3, somewhat in that order of magnitude. Now, if we put n equal to a quarter in here, then we will find that the product of this is equal to 2.8, somehow in this order. So it's really consistent with the experimental observation. It just shows you how self-consistent that spectrum is with all the observations, with all the calculations, and that's very, very nice. So in summary, the BSW spectrum has 4 parameters. It has the plateau modulus. It has the longest relaxation time. Then it has a characteristic time for the transition to the glass. And it has the scaling parameter. None of those parameters are new. They are all given in experimental data. You get the plateau modulus from G prime. You get the cutoffs from G prime, G double prime. You get n from G double prime. So no new parameter is introduced when writing that spectrum. There's no additional fitting parameter. And that's also interesting to note. Now, the pattern is somewhat self-similar. Somehow relaxation of those long molecules are the same on large scale and smaller and smaller and smaller scales. And that's probably the reason for the success of scaling theories in polymer physics. And so that's very supportive. And I just want to stress again that this result is independent of our conversion method. It doesn't depend on the parsimonious model or anything. We are really comparing the spectrum directly to the data. And you can see that the spectrum is a direct representation of the data. And from calculations, you can see that the whole picture is quite self-consistent. And that's it for today. Thank you. We have to look at branching now or distribution.